Okay, I guess we'll begin in a minute now that Lauren has arrived. Good morning, my name is Jeff McKenzie. I'm the Secretary of the Canadian Geophysical Union, and I'm going to be introducing today's lecturer, who is not only the Plenary lecturer, but also the Woo Lecture. The Woo Lecture is a lecture that's part of the hydrology section of CGU. Just a little bit, if you don't know about Hock Woo or who Hock Woo is, he's a very eminent hydrologist and researcher in Canada. For the past 40 years, I've been studying primarily cold regions hydrology, in addition to a lot of other stuff, looking at his CV this morning. And he really has what I think stands out, not just amazing research, but also has an army of graduate students over the past 40 years. Many of people in this section of hydrology at CGU are either his sort of direct students or sort of called academic grandchildren, sort of populate a lot of CGU. And so this lecture was really named in honor of him. And so that's sort of the background on this lecture. Today's speaker is Professor Laura Lautz from Syracuse University. I've known Laura for a long time. We were just talking about this the other day. I think I've known you since 2002. She's a professor and now department chair at Syracuse University in the Department of Earth Sciences. She's a hydrogeologist and a hydrologist. Her early research started out looking at hyporheic zone mixing, sort of this interaction of near stream water with streams, and also how this fits into a bigger picture of groundwater, surface water interactions. And then from there, she's taken that sort of framework that she developed there and did a lot of stuff looking at temperature as a tracer of groundwater systems and groundwater surface water exchange. Some applied work looking at like how cattle ranching or beaver dams affect groundwater surface water interaction. And also done a lot of international work. She's worked a lot, in fact, in collaboration with me in Peru, and just came back a couple days ago from Rwanda in Africa on a project. And finally, in the past sort of, 5 to 10 years, Laura started to work a lot on questions related to fracking. So this is extracting non-conventional, mainly methane from the subsurface for oil and gas. And that's what she's going to talk about today, is salinity and methane in groundwater of the Marcellus Shale region. Thank you, Laura.
Okay, good morning everybody, and thanks so much for getting up early to join us for the presentation today. And thanks, Jeff, for the introduction. So my talk today is a bit about shale gas, hydraulic fracturing, and water quality. I had a slide in here to talk a little bit about Hock Woo, and this being the Woo Lecture. This was a good opportunity for me to learn more about Hock Woo and the legacy that he's left on the hydrologic sciences. And just a couple of additions to Jeff's introduction. Hock Woo bridged different areas of hydrology, and I guess I wanted to put my talk in context and thinking about the contributions Hock Woo has made and how my presentation might speak to some of those things. So he used stochastic and statistical methods for hydrologic problems, and advanced work combining empirical, experimental, and observational studies with deterministic and stochastic modeling. And so the work today that I'll be presenting, I hope, speaks to some of those topics that he's advanced within our discipline. Before I get into the presentation, the work that I'm presenting is a highly collaborative project. And so I want to acknowledge some of those collaborators and contributors. So this work, affectionately called Project SWIFT, that's our acronym, Shale Water Interaction Forensic Tools, was conceptualized by Greg Hoke, Zoon-Lee Liu, Don Siegel, and has contributions from John Kessler, John being from the University of Rochester, the others from Syracuse. And of course, all the work that I'm presenting has been made possible by the contributions of a number of different students at all different levels. High school students, undergraduate students, community college students, graduate students from different universities, and I think you'll see that effort reflected in the presentation today. We also work a lot with homeowners, and so we have engaged with hundreds of homeowners in 5 counties of southern New York, Steuben, Broome, Tioga, Chemung, and Chenango counties, and so I want to acknowledge their contributions too. And then of course, this project, nothing's possible without some financial support, and that's from a combination of sources, including the NSF, Syracuse University. Okay, so before kind of getting into the water quality work that's the centerpiece of the talk, I wanted to provide a little context for the Marcellus Shale. I'm sure you've all heard of the Marcellus Shale. I'm sure you are all familiar with hydraulic fracturing and shale gas. But the Marcellus and Utica Shale are really kind of at the center of the shale gas hydraulic fracturing debate and discussion in the U.S. So this plot shows natural gas production and consumption in the last several decades, and you can see this spike in natural gas production in the past 10 years, to the point where in the US now we produce as much natural gas as we consume, and we are actually becoming net exporters of natural gas, which is a real change in the energy landscape in New York, or I'm sorry, in the United States. And this is really driven almost exclusively by increases in shale gas production. So this shows from 2000 and then includes projections out to 2050, but this shows that shale gas is becoming the dominant source of natural gas production in the United States, and that's just projected to continue into the future. So shale gas is the story. And I looked sort of briefly thinking, well, I'm very US-centric in this talk, and maybe that makes sense because I'm talking about the Marcellus and Utica shales, but trying to put the US energy landscape into perspective. So these are projections for natural gas production for the next several decades, and you can see the growth in natural gas production in the United States that's projected relative to rates of natural gas production in Canada. And you can see that all of this is driven by shale gas. So shale gas is like the story of natural gas production in the US. So shale resources and shale production are found in many different places, but in the US there are really 7 plays that are the most prolific areas of shale gas production. And so these are names that are in the news all the time: the Bakken, the Permian, and of course the Marcellus Shale. And if we look at shale gas production over the past several years from these different plays, you can see how the Marcellus and Utica Shale, not only is shale gas the center of the story, but the Marcellus and Utica shales are also the center of that particular story. So I guess there's no laser pointer, so I'll just try to walk you through this. So you can see the different shale gas plays are in different colors, and the green is the Marcellus and Utica Shale. And basically at this point, the Marcellus and Utica Shale are producing pretty much half the shale gas in the US, which is continuing to grow year after year. Okay, so what does that look like in real time? Wow, thank you so much. Thank you so much. This will be helpful for me. Okay, which screen? All right, so I love this animation. This is comes out of Penn State at the Marcellus Center for Outreach and Research. And this is an animation of unconventional gas wells drilled each year starting in 2004 to 2016. And you can just see the kind of explosion in gas well drilling through 2016. And I just want to point out a couple things. So this is Pennsylvania, which has been kind of the center of the discussion here and most of the activities in Pennsylvania. But we also have West Virginia and Ohio, and shale gas wells have been drilled in all of those states. And you can also see there's a real high density of wells being drilled in northeastern Pennsylvania in these 3 counties that include Bradford County that gets a lot of attention. But there's one thing that's conspicuously missing from this map, and that is any drilling of wells in my home state of New York, right, just north of the New York-Pennsylvania border. And that's because in 2014, our governor, Andrew Cuomo, passed legislation that bans hydraulic fracturing in New York State. So we don't have any horizontal wells or hydraulic fracturing in our state, and that's the only state in the Marcellus and Utica shale plays, right? There is drilling in Pennsylvania, West Virginia, and Ohio. And this was really driven, actually, the articulated reasons for this at the time this legislation was passed was that there were health concerns. They'd kind of studied the potential health impacts of hydraulic fracturing, and that was one of the primary justifications for the permanent ban. And there are a number of environmental concerns that people have around this issue, around shale gas and hydraulic fracturing. And that's kind of what I'm speaking to today. So the environmental concerns for shale gas production include the topics that are near and dear to my heart, which are groundwater and surface water interaction and water quality. And there's concerns for potential contamination of groundwater and surface water from the fluids that are injected during hydraulic fracturing, from the potential for the gases that are being produced, the methane, to migrate into shallow groundwater aquifers, and also for the production of natural gas, which also produces a lot of water, to produce naturally occurring chemicals that are found deep within the subsurface and bring those to the surface and introduce them into surface and groundwater systems. I think this is also amplified in the Marcellus and Utica shales because many of these areas are actually rural areas, and so most of the people who live and work in these areas of Pennsylvania, West Virginia, and Ohio, they all have private wells that they use for their water supply. They're not on municipal or city water supplies. And so there's a lot of concern, a very personal concern about the quality of their water, which of course affects their livelihood, property value, health, etc. So these things kind of intersect and really amplify, I think, these environmental concerns. So again, I'm sure you're all familiar with just the concept of hydraulic fracturing and horizontal wells, but just to point out a couple things to keep in mind for the presentation, I like this diagram because it shows the idea of a well being drilled vertically and then of course turned horizontally along the shale gas layer, and the concept of injecting these fluids and fracturing the shale and the gas and water migrating to the surface, but it also highlights a couple of important points. And one is that the depth of hydraulic fracturing these shale gas wells is typically high, could be thousands of feet or beneath the surface, and this is really deep, particularly in context of the shallow groundwater aquifers that these private wells and even municipal wells are tapping into. So this is obviously not a diagram to scale, but it's trying to give you a sense of scale of what are the sources of water for municipal and private wells, and how does that relate to the depths at which hydraulic fracturing is happening. Okay, so I also, I mentioned that these areas are rural. This is another one of my favorite sort of maps showing information about this issue. This shows the counties in the United States, including areas of the Marcellus and Utica Shale, and the density of wells that are drilled in these counties. So the darker brown colors indicate more hydraulically fractured wells in those counties. And then the ones that are highlighted in blue are counties where 30% or more of the population gets their water from private water systems, and also where there are more than 400 hydraulically fractured wells. And so I just want to draw your attention to these three counties in northeastern Pennsylvania where there's lots of hydraulically fractured gas production wells, and also a large proportion of the population that's relying on private water for their drinking water supply. So this is really like the intersection of these issues. So a little bit about the hydrogeology of this area. This is a conceptual diagram from a USGS circular by Heisig and Scott. And this is a really nice kind of visual of what the hydrogeology looks like in northeastern Pennsylvania and southern New York, in areas overlying the Marcellus and Utica shales. And what we have is, we have some topography here, and also at depth, you find very salty Appalachian Basin brines. And so the water at the depths where shale gas is produced is very salty, and then that transitions to the freshwater system, which is what people are tapping into for their private water supply. And so based on this conceptual model, depending on where you drill a water well, you can start to draw water out of the ground that might naturally interact with this system. You might drill a well in a lowland area, maybe where there's some natural fracturing or like preferential flow paths in the subsurface that would allow the brines, which are charged with methane, to naturally migrate into shallower groundwater aquifers where they can be introduced into people's water supply, which is something happening sort of in the background. And then we're overlaying the hydraulic fracturing, gas production, produced water on top of that. And so deconvoluting what are natural variations in water quality and what kind of changes in water quality might be introduced by hydraulic fracturing is a non-trivial task, and that's kind of what I'm talking about today. So originally when we started this project back in 2014, 2012, sort of spin up during that time, we had anticipated that hydraulic fracturing was coming to New York State. And so we thought we've got to get out and get some baseline water quality data before the shale gas production begins. And it's still possible that hydraulic fracturing will come to New York State. The political landscape is always changing, but at the moment we have a permanent, however permanent can be, we have a ban on hydraulic fracturing. So we've used this opportunity to use our study site, which is these 5 counties of southern New York, to do kind of a control versus treatment assessment. So it's sort of an interesting experiment that's happening where just north of this border, there's no unconventional gas production, and immediately south of the border, there's a lot. And the geology and climate of this area is the same. And so it's an interesting chance to sort of look at the New York is pre-hydraulic fracturing, so we can look at it as such and then compare that to what we see in Pennsylvania. Okay, so I'm going to address 2 research questions today, which I've been working on in the context of water quality and trying to think about how we could fingerprint potential water quality problems associated with hydrofracking from natural variations in water quality that we see in the absence of hydrofracking or shale gas production. So one question we wanted to ask is, if domestic well water is saline, so if someone has well water with a high salinity or high TDS, could we figure out if that salinity were due to the introduction of produced water? So if there were produced water, maybe you had a spill or leakage from a holding pond at the surface, or some way that produced water would get into the environment, could we tell the difference between that salinity and the natural sources of salinity and some unnatural sources of salinity in the groundwater? So we'll look at that. And then also, there's a lot of concern. I mean, my opening slide had a picture from a movie called Gasland. I've never actually seen the film, but I've seen the picture of the gentleman on my title slide lighting his tap on fire. This is methane in groundwater. And there's a lot of concern and public attention on that issue. And so how could we anticipate where we might find naturally occurring methane in domestic wells versus methane that might be introduced by hydraulic fracturing? Okay, so in order to answer those questions, we, for this project, went to southern New York and went into people's homes and sampled their well water. And that seems like a simple task, but this involved writing thousands of letters and making hundreds of phone calls and putting an ad on the local NPR station and just trying to get people to respond to our inquiries and allow us, into their basement to sample their well water. And so sometimes I tell people, think about what's in your basement and whether you would want me crawling around down there if you didn't know me. So we've seen quite a number of interesting basements, but so we eventually got over 200 people to allow us to do this. And one thing we do is we give them water quality reports. So this is an example of a report that we've provided to a homeowner where we show them how their well water quality compares to the couple hundred homes that we've been to in their area, so they can see if they have different water quality than their neighbors and how their water quality compares to any applicable standards. So we provide this for free, of course, because they're giving us the opportunity to test their well water for our project. So this is one of my graduate students with a homeowner actually teaching the homeowner how to sample his own well and send us those samples for analysis. I also mentioned that this project relies on lots of students, so this is just a very quick acknowledgement of all those high school, community college, undergraduate, and graduate students that are really the ones going down into those basements and sampling water and then bringing it back and doing all the analytical work. And it's actually been a really fun project to work on with those students. Okay, so to the science. So for Project SWIFT, we've gone to 203 domestic wells in southern New York, and we have sort of a structured randomization where we have a grid over our study area, and we randomly select wells within the grid, and then of course we try to get those folks to allow us to come into their home so that we have good spatial coverage, but the samples that we have are random. Like we don't know anything about the wells before we sample them. We're not targeting like specific types of wells. So it's supposed to be a representative distribution of well water quality in southern New York. So the red dots are all the homes that we've been to. The blue dots are homes that have been sampled through a USGS water quality program, just to give you a sense of like data density in our study versus some others that have done similar things. Okay, so the talk is kind of broken into two parts, one looking at the salinity question, and then one looking at the methane question, and then wrapping it all up. Okay, so we're, obviously lots of people are working on this issue, and we're just one study, and I would say not as much attention in New York, but there's a lot of attention in Pennsylvania on hydraulic fracturing and water quality. So this is a nice paper from 2012 by Nat Warner and colleagues, and they sampled pre-hydraulic fracturing well water quality in northeastern Pennsylvania. So this is the New York border, so we're just south of our study site. And what they did is they looked at shallow groundwater samples, and they argued that we find natural migration of Marcellus formation waters, or these Appalachian Basin brines, into shallow groundwater aquifers in Pennsylvania, and they deduced this by looking at concentrations of bromide and chloride in shallow groundwater samples and how those compare to chloride and bromide concentrations in the brines themselves. And so they show that these samples with a red color, these have bromide and chloride ratios or relative concentrations that seem to show a mixing line upward towards those formation brines, and this is evidence that there are some small proportion of the sample that comes from the formation water brines. So just to give you, if you're familiar with that paper, this is the exact same analysis of our own data set, just using the same symbology and scales and everything to show you that the New York data that we have is very similar to the Pennsylvania data, which is not surprising because they're literally right across the street in some cases. But I guess I want to add some complexity to this story, which is really what I'm trying to deal with, where one could argue that again we have water samples here that look like they're mixing with these formation water brines, but I could put other sources of salinity on this graph that I think complicate this image. So these are samples of road salt runoff. So we've collected runoff from roads during the winter, looked at the salt, and these are in different areas. Some of this is in New York and some in other places, and it's highly variable because sources of salt are different in different places. But the bottom line is they look different, but when you start to really try to parse out what the source of salinity must be in these shallow groundwater samples, I think it's not super clear that they're from formation water brines. And then there's also septic effluent. All of these homes have septic systems, and so there's salinity introduced into shallow groundwater from septic effluent, and those really kind of muddy the picture a bit. And so one thing I was interested in is, could one parse out what the most likely source is of the salt and distinguish between these different sources using chemical fingerprinting? And of course, I'm not the first one to ask that question. There's lots of folks who've tried to do this. This is another study different from the Nat Warner one. This is a study by Pano and others back in 2006. Excuse me. And they also looked at chloride and bromide ratios in water samples to try to fingerprint the sources of salinity in those samples. And so you can see they created this nice field diagram where you could take a point and plot it on the field and then figure out what the source of salinity is. So, and they used these data points to generate these fields. And so to give you a sense of the challenges that I'm thinking about, my goal is to say, okay, if you gave me one of these samples, one of those white dots, and I put it on, the graph, could I tell the source of salinity? So I would encourage you to look at the dots, look at the fields, pick one, maybe even pick one that's a little bit ambiguous, and think, okay, that plot's in the road salt field or septic effluent field, I'm gonna assume that's what that is, right? But then if I show you what they really are, because these are all samples with known sources, you were probably right. Maybe you picked one that came out right, but if you were especially down in this area here, it's a little bit uncertain. And also these are sketched lines. They're not lines that I have an equation for. Like I've just sketched them in PowerPoint based on the graph in the paper. So, you know, it's difficult for someone to give me a sample and for me to say, oh yeah, that's road salt. It's not that easy actually. So I guess my thought from this was, why would we limit ourselves to just looking at these two halogens, chloride and bromide, when we measure lots of things in these water samples? So this is meant to be impossible to read, to give you a sense of having lots of data, so don't worry about the details, but this shows like all the solutes that I used in this application that we measured in these 200 homeowner wells. And you know, the chloride and bromide plot is just one of these. So there's lots of different relationships that we could use to try to fingerprint sources of salinity besides just chloride and bromide. So that's what we do. And so just quickly, I'm going to show you a model that we've developed to try to more definitively fingerprint sources of salinity based on their chemistry. And basically what we do is we generate synthetic data or training data by using a very simple two-component mixing model and taking sources of salt, mixing them with shallow groundwater artificially, you know, like in our minds or on our computers, and making training data sets of what we think that chemistry should look like. And then we train a statistical model, a classification algorithm to discriminate between those groups, and then we use that to determine sources of salinity and unknowns, and we've used validation data to try to assess how well that model works. So it kind of looks like this. You can imagine we have our road salt or our animal waste. Fortunately, we don't have to do this for real. We just do this on the computer. But we know the distribution of chemistry in animal waste. There's actually some pretty good literature on that. And we know what low salinity groundwater looks like. So if we poured a little animal waste into our shallow groundwater, what would the chemistry look like? And so this is an example. The lower right here is just one plot of some training data. So it's synthetic data, but you can see these different clouds that show different populations that have different overall chemistry. And this shows chloride and bromide, but I could have shown many different plots of this water chemistry. So we train a multivariate statistical model, and I put this in here not to belabor the statistics too much, but maybe folks are familiar with principal component analysis. I think that's probably one of the most commonly used multivariate statistical tools, and basically you feed a data set into principal component analysis, and the goal is to create just a couple of linear combinations of the original variables that explain a large portion of the total variance. And so you can take a 9-dimensional data set and reduce it to the 2 dimensions. Linear discriminant analysis is basically the same thing, but rather than trying to just explain variance within one sample or one population, we're trying to use those linear combinations to separate groups and discriminate between groups. And so we do that in this case. So this is the product of that modeling exercise, and this shows a plot of 2 scores, which are linear combinations of the original solute concentrations, and so they're a function of those. And I've given them just my interpretation. You can do this in statistics, in multivariate statistics, and just try to explain what I think these represent. And so, like, the one score is very much related to the bromide concentrations, so I'm calling this a Brine score. And one is very much related to the chloride concentrations, and one to potassium, so I can sort of interpret what they mean. And you can actually see the arrows showing those are hard to read, especially if you're sitting way in the back, but you know, we can look at how these scores correlate to the original variables. But regardless, I've got different clouds here that show these different sources of salinity: road salt, basin brines, organic waste. And so now I can do the same exercise where I can put points in the field, just like with the bromide to chloride plot, and then I can fingerprint them in the same way, but it's more definitive, and that the discriminant analysis like draws a line in the sand, if that makes sense, for you to classify samples. And so we've tried to validate this, because it's tricky actually. You know, you can train this model and you can fingerprint unknowns, but how do you know that that's correct? And so we applied our model to a data set that I mentioned earlier, this data set by Pano and others, where they looked at bromide and chloride ratios to fingerprint salinity. And they have a really beautiful data set of water samples contaminated by different contaminants. And so we can look at samples that we know to be contaminated with basin brines and know to be contaminated with road salt and we know are contaminated with animal waste, and then we can see whether our model gets it right by throwing those into the model. And so we did that, and this is just similar maybe to it's very similar to the bromide chloride plot earlier. These are all of our this is all the validation data. So we know the source of salinity, where those points fall in our field, and which ones were labeled correctly and which labeled incorrectly. And for time, I'm just sort of showing you this as a demonstration without getting into the nuances of it, but the idea is it's just like using ratios or halogens, but we have a definitive way to classify, and we have used validation data to assess that that's effective and to get a sense of the confidence that we can place in these classifications. So then of course, the most interesting thing is to actually apply this, and what did we learn? And so if we look at our 200 homes in southern New York, and we look at those that have relatively high chloride concentrations, we can infer the source of the chloride based on our model, and we've done this. And so the bottom line is, in New York, where there's no hydraulic fracturing shale gas production, our homeowner wells, when they have salty water, about a third of their high salinity wells, the salinity is from mixing with Appalachian Basin brines. So perhaps those wells are near that transitional zone between the freshwater aquifer and those deeper brines. And so this will make it difficult to determine in the future if formation brines have been introduced, because they're already there presently. And so we can fingerprint them, but we also have natural mixing of these brines with shallow groundwater. Okay, so kind of the next part of this is to look at the methane concentrations. And I think this is an area that sort of more recently has gotten the most attention. And so we're again in New York, and so what is the natural occurrence of methane in shallow groundwater in New York, and how does that compare to Pennsylvania? And if you're familiar with this literature, even loosely, you may have heard of a couple of controversial papers about this topic that have titles like "Methane Contamination of Drinking Water Accompanying Gas Well Drilling and Hydraulic Fracturing." So paper are arguing that there's methane contamination as a result of hydrofracking. And then a follow-on paper saying methane concentrations in water wells are unrelated to oil and gas production in the same area. So there's clearly different conclusions folks are drawing from very similar types of data about whether hydraulic fracturing has introduced methane into shallow groundwater. So we're gonna look at New York, which is a less politically charged place to look at methane concentrations in shallow groundwater aquifers, but very relevant to what's going on in Pennsylvania. So again, this is our 5-county study area and our couple hundred homes, and what we see in terms of methane occurrence in our homeowner wells. And so to give you some context, so what is considered high methane? So above 28.6 milligrams per liter of methane, the water is saturated with methane, and above that concentration you start to get degassing. So like we have some homeowners where their water is effervescent, right, because it's so charged with methane. Between 10 and 30 milligrams 10 and 28 milligrams per liter of methane, this is usually given a cautionary, moderate hazard rating as a water quality standard, but that would be a high, elevated concentration of methane. And then below that, maybe more kind of benign concentrations. And so this is showing the areas in the samples in yellow and red are places that have over 1 milligram per liter of methane, and in red over 10. And so you can see between 2 and 5, well, in our case it's 5%, but in other studies people see the same frequency, 2 to 5% of wells that have more than 10 milligrams per liter of methane. And this might not be surprising, because if we go back to our conceptual model, if this water is charged with methane, and there are pathways by which that methane can migrate into shallow groundwater aquifers, then if we punch a well into the ground and pull that water out, maybe it's not surprising that we do get methane. And we might be able to predict where that would happen naturally. Perhaps it happens in lowlands and valleys because they're closer to that transitional zone. Maybe it also happens in wells that we think are pulling some water that is mixing with these brines. So maybe there's some characteristics of these wells that we could use to predict where we would find methane naturally. So there's a lot in the literature about methane occurring in valleys, preferentially occurring in valleys. And I grabbed this screenshot because I literally did one day Google what is a valley. And I did this because it sounds like a ridiculous question, but when do you leave the valley and enter the upland? Where's the line? And so if I have a well and I put it on a topo map, how do I classify it if it's a binary classification? So we all know what a valley is, of course, but they're tricky to define. And so people have used different ways of defining valleys in the literature. People have done slope and relief analysis using DEMs. That's a USGS approach that they've used to distinguish valley wells from upland wells. And so we did that in our study site, and you can see the map, and the blue are valley wells and the yellow are upland wells. And the details don't matter, just the idea that we would do this. There's other studies that have used proximity to National Hydrography Database flow lines. So if you're near a river, you're in a valley. If you're not near a river, you're in an upland, and getting a cutoff that way, and different distances, 1,000 feet, 500 feet, because these are US publications. And so, so we've done that, and if you compare these, you get different classifications. So they don't yield the same result. And then another study in the literature used mapped valley aquifers to say whether things are wells or uplands. And anyway, so we've tried this all. And here's what we find, is that if you use this relief and slope analysis that the USGS has done, you don't really see any difference overall in the methane concentrations in wells positioned in those two areas of the landscape. If you use the flow line analysis, you see that the valleys indeed do have higher methane, but it's really weakly significant, so one could argue about that, I guess. And then these mapped valley aquifers show that the uplands have more methane. So, it's tricky to figure that out. Okay, but if we keep going, maybe it's the water type. Maybe it's these wells that are pulling water that has more sodium, indicating mixing with these basin brines, as opposed to the calcium bicarbonate water that we typically find in the upland areas and the more freshwater wells. And so we've looked at whether the water type is correlated with methane concentration. And so these are our homeowners and the different water types, and then the distribution of methane concentrations. And we do see that when when sodium is the dominant cation, the methane concentrations are higher. So there does seem to be a relationship between the water type and the methane concentration. So, so this is all interesting. We can look like, is it this variable? Is it that variable? Is it this one? Which one's the best predictor? But maybe you could see that if I know your water type, I still don't really know whether you have high methane or not. It's not a very definitive predictive tool. Certainly the valley business is not very predictive. So how do we get at a predictive model? And so I was interested in how these variables might interact. And so this gets me back to statistics, using applied statistics. And so, but these are also categorical classifications. So, we can't use we could use different techniques, but like a simple regression model, right? These are binary variables, so it's like a little tricky to figure out how to integrate maybe a continuous variable with a classification and some somewhat qualitative categories. So we tried to use a technique called decision tree learning. It's like machine learning or data mining. And for those not familiar, I really love this example of decision trees. This is a decision tree that's like commonly used as an example of this kind of analysis. And this is a decision tree showing who survived on the Titanic. Okay, so this is where you take the manifest from the Titanic and look at variables for the individuals on the Titanic, whether they were male or female, their age, whether they were with other family members, different demographic information, and then use that to try to develop a model to predict whether that individual would have survived or perished on the Titanic. And so when you feed that manifest into a decision tree learning tool, you get the following flow chart. So this is something derived from the data. There's no, like the machine learning doesn't know anything about the Titanic or the people on the Titanic, right? This is just the most efficient way to bin people into whether they survived or not and create the most efficient predictive model. So the first question you need to ask to make this prediction is, was the passenger male or female? And if the passenger was female, that's actually all you need to know. 36% of the people on the Titanic were female, and 73% of them survived. So that's a pretty good predictor about whether you survived on the Titanic. If the answer is yes, this is a male passenger, then we need more information. We need to know the age of that person. If the person was older than 9.5, then that is a good, an adult male, that's 61% of the passengers on the Titanic, only 17% of them survived. And then if it's a young person, we need to know, was that person with siblings or with a family? And if they were, then they were unlikely to have survived, and if they were not, then they were likely to have survived. So I guess the bottom line here is this is a completely empirical model, but it jives with our conceptual model of decision making on the Titanic, and that it shows that the data suggest women and children were saved first, which is our conventional wisdom, and the data actually bear that out. So when we're looking at methane, which is maybe a little more of a benign decision tree, well, maybe it's more, maybe, I don't know, then what is the most efficient way to bin wells into categories to figure out whether they would likely have methane occurring naturally or not? And that's useful because although it's completely empirical, it can affirm our conceptual model or show that there's an alternate conceptual model that we should apply. So this is the decision tree for our data set in New York, where, and actually this is integrated with other data because you need lots of information to train a model like this. So we put in 658 observations from New York and Pennsylvania. They're all pre-hydraulic fracturing. And if you look at all those wells, 7% of them have methane concentrations that are over 1 milligram per liter. So that's what this pie chart shows, right? We have 658 wells, 7% of them have more than 1 milligram per liter of methane. And then we can bin them, and this is not my arbitrary binning. This is a computer algorithm, a statistical model that's trying to figure out the most efficient series of pathways to bin samples. And so the first division here, and the arrows here, their thickness shows the number of samples that fall down the tree in this way. That most samples, sodium is not the dominant cation, calcium is. And if calcium is the dominant cation, you go over here, these are all those wells. There's 535 of them, but only 2% of them have methane concentrations over 1 milligram per liter, whereas if sodium is the dominant cation, about half of them do. And then although the valley-upland distinction is not super predictive on its own, it does show up here as having some predictive power in this category. So in other words, if a well has sodium as the dominant cation and it's in a valley, then 56% of the wells have methane above 1 milligram per liter, and if it's in an upland, only about a third. And so this is still something I'm interested in developing further, but the idea is, could we predict where natural methane occurs so that if you see elevated methane concentration in a home with this water type, maybe that's unusual, and maybe that would be an indication there's something unnatural that we could attribute to the source of the methane, and so we could get at that kind of probability. Okay, so in summary, high salinity in domestic wells in southern New York and in the Appalachian Basin, in areas overlying the Marcellus Shale, I should say. High salinity is common, and it's also commonly due to natural mixing with Appalachian Basin brines. And high methane is also somewhat common. 2 to 5% of wells have naturally occurring methane. And we tend to find that methane in wells that are positioned in valleys and tap sodium-rich waters. And we think that's because of the saline groundwater that's also charged with thermogenic methane mixing with shallow groundwater. So I should have said, like, going back to this is a purely empirical flow chart, but it jives with our conceptual model. So it makes us think this has some process behind it. It's not just, it's empirical, but we can explain it. It jives with what we think we should see. But I think it does remain a challenge, and I think it will continue to remain a challenge to predict whether methane or salinity is associated with shale gas, because we also have these things occurring naturally, and not only trying to fingerprint the source of the salinity, but also whether that is due to shale gas activity or not is a really challenging undertaking. So with that, thank you for your attention, and I'd be happy to take any questions. Thank you so much.
Yeah, we have time for a few questions, I think. Yes. Yes.
Are you going to move towards looking at isotope ratios of any of these, anything?
Okay, so the question was, will we look at isotope ratios of anything that we've measured? That's a good question. So there's two parts of that. So on the salinity side of it, some folks have used strontium isotopes to try to fingerprint different sources of strontium and associated salinity. But we find there's basically in the samples that we have measured strontium isotopes, there's just like zero variance in our data set. So I don't know why that is, but in frustration I haven't explored it further. But it did occur to us, but I haven't really advanced that. So there is that. On the methane side of things, there's lots to look at in the methane itself to determine whether it's biogenic in origin or thermogenic in origin, which could be very useful. Again, I find those fingerprinting tools to seem really, really good on paper. You have a carbon and hydrogen isotopes of methane plot, and you have these different fields for thermogenic and biogenic, and I think there's a lot of ambiguity there sometimes. But there are, if you look at multiple things like the carbon and hydrogen isotopes of methane, and also higher order hydrocarbons, for example, you can get it whether it's thermogenic or biogenic. So we have done that. We haven't published that information on our methane data, but I have a graduate student right now, who you know, Caitlin, who's been going out to our homes once a month for the last 13 months and collecting methane water samples, looking at the methane, and looking at how the methane concentrations change seasonally in our homes, but also looking at the isotopic composition of the methane, the higher order hydrocarbons, to try to get at not only whether the methane changes through time, but to dive deeper into the source of methane. So methane isotopes, very useful, something we're looking at, and there are some ideas behind the salinity story, but I have to admit we haven't explored those as much.
Go ahead.
So yes, for your salinity analysis, for your training data, you assumed a binary mixing with the different sources. And I was curious if that's sufficient to distinguish the possibility of ternary or multi-component mixing in your solution.
Yeah, that's definitely an issue in that we have a hard enough time with just single source identification. So in other words, assuming there's only one source of salinity and that we can fingerprint it, and of course there might be multiple sources, and I could go back. We have some samples that the classification is pretty ambiguous, and we're thinking, oh, well, there could very well be multiple sources. It could be both some organic waste and mixing with formation brines. I think the trick is, of course, the more you allow for that mixing and then try to differentiate those populations, of course, it loses its effectiveness. So maybe I would say that the method is only going to be effective when you do have a single dominant source. Maybe that's what I should say, a single dominant source. So it's an issue, I think, it's an issue for all of these methods, and so there's kind of that. It's a tricky one. It's a really good question. I have no easy answer besides to acknowledge it's a limitation. Yeah, good question.
Time for one last question. Peter in the back.
Great talk. I was curious, do you think all the methane transport in the system is happening in a dissolved phase, which was really sticking with its groundwater, or you mentioned some gas is effervescent, so you have some gas phase diffusion and can transport methane from one groundwater type to another?
That's another really great question, and one I'm afraid I'm not sure I have an answer to. You know, I don't know. We do, so if the methane is associated with deeper brines, and so we commonly find them together. Of course, we also find the methane, and methane that looks very thermogenic, not biogenic methane, in calcium bicarbonate water. So there must be some other there must be transport of methane, not always with the original source water in which it's found. I mean, that must be true, right? Methane migrates, and that's why we can find, you know, reservoirs of methane that we can tap into and produce. But yeah, I think that's a tricky one. I mean, that would just make I think our classification model less effective if those things, you know, frequently decouple. But it looks like they often stay together, or they're at least correlated. Yeah, so it's a good question.
All right, I think we should, just for the sake of the timeline of today, we should continue on. One brief announcement. Just remember there's the banquet tonight, which always is a fun event. I encourage you to attend. And just again, thank you to Laura. We have a small gift for you, but thank you, Laura, for providing the video.
Thank you very much.